Hello, and welcome to Section 8.2 on the area of a surface of revolution. Recall that a solid of revolution is a solid region obtained by rotating a region in the xy plane around a line, called an axis. We will now do the analogous thing, but instead of rotating a solid region, we will be rotating a curve. The resulting object is called a surface of revolution. The goal of this section is to compute the area of a surface of revolution. The idea will be similar to the way we computed arc length. We wish to begin by approximating the area of the surface using objects that we know how to compute the area of, and then finish by employing a limiting procedure. Recall that to compute arc length of a curve, we began by approximating the length by approximating the curve with line segments. To obtain a surface of revolution, we rotate a curve about an axis. So if we approximate the curve by line segments, then after rotating, these line segments form bands. So if we are able to compute the area of such a band, then we can approximate the area of the surface. It is approximately the sum of the areas of all of the bands formed by rotating line segments. Let us begin by determining the area of a band. First, recall the area of a right cone. It is given by the formula A equals pi times r times L. This is classically derived by unwrapping the cone and thinking of it as a sector of a circle. If you have not seen this before, then do not worry about it and accept the formula. Now, how is a band formed? A band is obtained by removing a smaller right cone from a right cone, as illustrated by the figure. The resulting green band on the right is formally called a frustum. Since the frustum is obtained by removing a right cone from another right cone, its area should be the area of the larger cone minus the area of the smaller cone. More precisely, if the larger cone has a base with radius R and has height L1, and the smaller cone has a base with radius r and has height L2, then the area of the frustum is given by A equals the area of the larger cone minus the area of the smaller cone, which equals pi times R times L sub 1 minus pi times r times L sub 2, which equals pi times R of L plus L2 minus pi times r of L2, where L is the height of the frustum. We will now rewrite this expression in a much simpler form. First, note that the right equality can be rewritten as A is equal to pi times R times L plus L2 minus pi times r times L2, which equals pi times R squared times L plus L2 divided by R minus r squared L2 divided by r. Now observe that we have two similar triangles in the figure. Hence, by similar triangles, we have that L plus L2 divided by R equals L2 divided by r. We input this into our equality. A is equal to pi times R squared times L plus L2 divided by R minus r squared times L2 divided by r, which equals pi times R squared times L2 divided by r minus r squared L2 divided by r, which equals pi L2 divided by r times R squared minus r squared, which equals pi times L2 divided by r times R minus r times R plus r. Now we have that L plus L2 divided by R equals L2 divided by r, and we can solve for capital L. L is equal to L2 divided by r times R minus r. Therefore, A equal to pi times L2 divided by r times R minus r times R plus r equals pi times L times R plus r, which equals 2 pi L times R plus r divided by 2. If we set R average to equal R plus r divided by 2, then the area of the frustum becomes A equals 2 pi L times R average. With this in mind, let us now find the area of a surface of revolution. For now, let us rotate a curve y equal to f of x, where a is less than or equal to x is less than or equal to b, about the x-axis. We can partition the interval a to b into subintervals of equal length, delta x, and in turn partition our surface of revolution into bands or frustums. The area of the green band is approximately 2 pi times the length of the segment P1, P2 times the radius. If we choose a sample point, x2 star, in the interval x1 to x2, then the radius is approximately f of x2 star, and the length of the segment P1, P2 is approximately the arc length of the piece of the curve connecting the points P1 to P2. Thus, the area of the green band is approximately 2 pi times the square root of 1 plus f prime of x2 star squared delta x times f of x2 star. We perform this procedure for every band. The area of the surface of revolution is approximately the sum of the areas of each of the bands. In other words, surface area is approximately the sum I equals 1 to n of 2 pi f of xi star times the square root of 1 plus f prime of xi star squared times delta x. Taking finer and finer partitions will make this approximation better and better. So passing to the limit, we obtain the following formula for the area of a surface of revolution. Surface area is equal to the integral from a to b of 2 pi f of x times the square root of 1 plus f prime of x squared dx, which equals the integral from a to b of 2 pi y times the square root of 1 plus dy dx squared dx. This is the area of the surface obtained by rotating the curve y equal to f of x, where a is less than or equal to x is less than or equal to b about the x-axis. You should remember this formula as the integral of circumference times the arc length. Let's do an example. The curve y equal to the square root of 4 minus x squared with negative 1 less than or equal to x less than or equal to 1 is an arc of the circle x squared plus y squared equal 4. Compute the area of the surface obtained by rotating this arc about the x-axis. Recall the formula for the surface area is surface area equals the integral from a to b of 2 pi y times the square root of 1 plus dy dx squared times dx. We compute dy dx is equal to negative x times the square root of 4 minus x squared. Thus, the integral becomes the integral from negative 1 to 1 of 2 pi times the square root of 4 minus x squared times the square root of 1 plus negative x divided by the square root of 4 minus x squared squared times dx, which equals 2 pi, the integral from negative 1 to 1 of the square root of 4 minus x squared, the square root of 1 plus x squared divided by 4 minus x squared dx. Simplifying the radicand, we obtain that 1 plus x squared divided by 4 minus x squared equals 4 minus x squared plus x squared divided by 4 minus x squared, which equals 4 divided by 4 minus x squared. And hence the integral becomes 2 pi times the integral from negative 1 to 1 of the square root of 4 minus x squared times 2 divided by the square root of 4 minus x squared dx, which equals 2 pi times the integral from negative 1 to 1 of 2 dx, which equals 8 pi. Now what if we decide to rotate the curve y equal to f of x, where a less than or equal to x less than or equal to b about the y-axis? Recall that you should be thinking of the surface area integral as surface area equals the integral from a to b of circumference times arc length. Notice that the radius of the red band is now simply the distance from the y-axis. Thus, for a given value of x, the circumference is 2 pi x. Therefore, the integral becomes surface area is equal to the integral from a to b of 2 pi x times the square root of 1 plus dy dx squared dx. Let's do another example. Set up an integral that computes the area of the surface of revolution obtained by rotating the piece of the parabola y equal to x squared from 1 less than or equal to x less than or equal to 2 about the y-axis. We have that dy dx equals 2x, and hence the formula becomes surface area is equal to the integral from a to b of 2 pi x times the square root of 1 plus dy dx squared dx, which equals the integral from 1 to 2 of 2 pi x times the square root of 1 plus 2x squared dx. Note that if instead we rotated the curve about the x-axis, then the integral instead would be surface area is equal to the integral from a to b of 2 pi y times the square root of 1 plus dy dx squared dx, which equals the integral from 1 to 2 of 2 pi x squared times the square root of 1 plus 2x squared dx.